Alrighty, gang, welcome back to Calc 1. Today is another fun day. I know I say they're all fun days. They are all fun though, right? Today we are going to learn something called the chain rule, which is our last differentiation rule. After you have this rule, you can, in theory, differentiate all the stuff. So yeah, we're gonna talk about the chain rule. I also want to spend a little bit of time playing around with some of the things that we did before. We'll be able to do that in the context of the chain rule for the most part, but I think it'd be wise just to start with one or two problems where we use the product and quotient rules and derivatives of trig functions, just to kind of warm up for the day. Before we get into any of that, I just want to talk for a little second about the test and the study guide, because that stuff is published now, and you know, it's always nice to make sure we're on the same page. So here we go. That's good enough. This is MAC2311, section number 004, which is Calc 1. The date today is the 31st of January, 2022. And today, we're going to learn the chain rule. Which is section 3.4. We're also going to just practice a little bit. Practice derivatives from 3.1 through 3.3. And we're also going to talk about the exam. We're going to start with that bottom element. Ooh, that's a badly out of focus camera. Come on now. There we go. Okay. So exam 1 is going to cover all the stuff that we've talked about so far, right? That's how midterms work. Specifically, we're talking sections 2.2 through 3.4. Right, so everything from the start of the semester, first homework actually came from 2.2. We talked about 2.1, but there isn't much in the way of actual problem solving to be done there through 3.4, which is the material we're going to talk about today. So I guess this falls under announcements. Exam 1 is 1 week from today. We mentioned this last week. Which is the 7th of February, 2022. And I released study guide 1 today. I also released your new homework, so you've got kind of 2 things to be working on this week. The homework, which is just covering 1 section, it's fairly short, and the study guide, which has examples of problems from all the sections that are going to be on the exam. The main thing I want to talk about is how you're going to get your grade for the study guide. So if I could draw your attention briefly to the syllabus for this class, I just want to remind you, study guides are worth points, right? A non-trivial amount of points. Each one is worth 25 points, which is about a quarter of an exam grade. The important thing to remember about the study guides is that while they are posted on WebAssign, to get credit for the study guide, to get those 25 points, you need to upload scans of your work. Right, all the steps to the Canvas assignment called Study Guide 1. So the purpose of the study guides is not just to be like a review. Of course, yes, it is kind of a review for the test. But the real reason we have these study guides is so you can show me your work before the test, and I can give you some feedback on that work. The study guides are graded for completeness only. Not correctness. So please don't look up solutions. As you solve the study guide problems, kind of pretend like you're taking the test, right? Solve them on your own. No Mathway, Wolfram, whatever. If you want to talk to a tutor, okay, but really try to solve them on your own. Once you finish solving the study guide problems, or have at least attempted all of the study guide problems at least once, whether you've completed the thing in WebAssign or not, go ahead and scan your work and submit it to Canvas. That way I can go in there and I'm not going to mark all the problems, but I'll mark a few of them the same way I would on the test. And that way, if there's like an issue, a notation problem, or a mistake, an algebra problem, something that I see in your work, I can put a little note here and be like, okay, on the test, this would be a 2-point mistake, and here's what you need to do to fix it. Or on the test, well, I want you to write this way instead of that way because this has some problems, whatever. The idea of the study guide is not just to be a review, but it's to allow me to see your work and to allow you to see how I grade stuff. Because you don't want any surprises on the test, right? You don't want to be like, oh shit, I didn't know you're going to take off points if I stopped writing the limit after the first line. You want to know exactly what standards I'm going to hold you to on the test. So don't worry about everything being correct in your work. More than wanting to see correct solutions, I want to see your solution. That way I can give you the help that you need to prepare for the test. If it's wrong, that's okay. I'm still going to give you full credit on the study guide as long as you've attempted each problem in the work. And then, of course, you want to see my feedback because that's how I'm going to grade your shit. So, please don't hack the study guide together with tutors and Mathway and Wolfram and stuff. Just solve the problems like you would on the test, on your paper. As soon as you've done that, scan that shit, upload it to Canvas. I can get in there and mark it up for you so you know what's good, what's bad, what will penalize you on the test, what will not, all of those sort of things. To scan, I recommend, if you have a physical scanner, that's awesome. But the apps that I've used with success are Cam Scanner and Adobe Scan. You will need to use a similar tool on the day of the test, because I do give partial credit. A lot of the test questions are free response questions. You'll need to scan and upload your written work for the exam as well. So the study guide gives you an opportunity to experiment with these apps and find one that you like prior to the day of the test. Again, if you have a physical scanner, you can use that. That's awesome. If you have an iPhone instead of an Android, the Notes app on the iPhone is actually really good at scanning things. The important thing is that you must submit a legible, high contrast PDF. And this goes for all the times throughout the semester when I'm going to require you to show me your work. What I don't want you to do is take a photo with your phone's camera, just a regular photo, use some hacky online tool to convert it to a PDF and submit that. That stuff really not very useful to me. It always comes out very low contrast. The colors are washed out. The lighting can really affect things. So use an app like Cam Scanner or Adobe Scan. They're free. They're free. They're fast. It's quicker than taking a picture and then converting to a PDF and then uploading. So play around with one of these apps or some other app. You can search free scanner app. If you find one that you like, please let me know, right? I didn't know about Adobe Scan until last summer when someone pointed it out to me. I always just use Cam Scanner. And use those to submit written work when it's called for. So again, to get credit for the study guide, it is not enough to answer the questions in WebAssign. To get credit for the study guide, you need to upload your solutions showing work to the Canvas assignment titled Study Guide 1. Once you do that, I'll get in there and mark them up, just marking a few questions in your study guide. There's 20 questions, marking a few of them as though they are problems on a test. So you can see how I grade, I can see your notation, we can kind of, figure out what it is we can expect from each other. And then the last things here, graded for completeness, not correctness. So please just show me your work. I don't want to see somebody else's work, just yours. This way there's no penalty for making mistakes. And then the apps that I've had success with are Cam Scanner and Adobe Scan. The Notes app, I understand, works well. And if you find something else, please let me know. But please don't take a picture and then convert it to a PDF. That will not give me a legible, high quality, high contrast PDF. Any questions on this? Yeah.
Is there going to be an answer sheet?
Okay. Microsoft Lens is apparently another good option for scanning. I'm not familiar with it, but is that on a Windows phone?
I don't know if it's Windows, but I use it on Apple, and I use it for my chemistry class. So
oh, yeah, very nice. As long as it produces a PDF and it's nice and high contrast, I'm happy. And then Isabella, what was your question?
I asked if there's going to be an answer sheet so we can see if our review is right.
Oh, good question. Well, so you'll be putting the study guide is actually in WebAssign. So when you type your answers in here, it will mark them as correct or incorrect for you. So on that level of detail, you will get a yes or no. If you want more detail about a particular thing, of course, I will mark some of the problems. But if you're like uncertain about one of the problems and it isn't one that I mark for you when you submit your work, just let me know and I can send you a solution or we can talk about it in office hours. I will release a full key for the test. So after the test is done and everybody's taken it, I will release the full key there with written out solutions, but I don't usually do that for study guides. Okay. Any other questions or comments? Okay, so we're all clear on how to get credit for the study guide. What I really want to avoid here is at the end of the semester, somebody who hasn't submitted any written work for the study guides going, well, I did it in WebAssign, doesn't that give me the credit? I want to make sure we all understand that in order to get those 25 points, I need the work. That's the point. The work, by the way, this is due at the start of the test. Now, if you hand it in minutes before the start of the test, you won't be getting feedback before the test, obviously. So I recommend you work on the study guide as soon as you can and submit it as soon as you can. That way I can get you feedback before the test. But if you're 100% confident, comfortable with your work, you know it's perfect, you don't need any feedback, the very latest you can hand in the study guide is at the start of the test, right? Just before the test begins. After the test begins, I won't take work for the study guide. Well, okay.
Is there a time that like all the homework is due? Like you won't give extensions for module 1 or?
The final exam, yeah.
Okay.
So the last day to submit any sort of material, homework, anything like that is the final. So we got plenty of time there. But certainly I recommend doing all the exam 1 homework before exam 1. But you can, if you need to, you can polish those up to the day of the final. All right, so today we're going to talk about the chain rule. Leading into that, I want to practice a little bit some derivatives that we've seen before. I haven't told you what the chain rule is yet or what it does, but maybe a reasonable introduction to the concept would be, this is a function where we could use the chain rule. What the chain rule is a tool for differentiating composite functions, where there's like an outer function and then an inner function, where you've plugged something into a function. So instead of sine of x, you have the sine of 2x. Instead of e to the x, you have e to the 5x, that sort of thing. Normally, chain rule works great. We don't know the chain rule yet, right? So one thing that you can use to differentiate this particular function is an identity. And I always like to bring trig identities in when we can. We know how to differentiate sine x cos x, tan x, etc., but not things like sine of 2x or cos of 2x. So it might look like we're in trouble at the start here, because I haven't shown you how to do this sort of thing yet. But there's something called the double angle identity for the sine function. Does anybody know what the double angle identity for the sine function is? Who was my guy last week? I think it was Robbie who had the sum identities for sine and cosine right there on the top of your head. You can get this double angle identity by thinking of it as the sine of x plus x. Now, I won't go through that derivation, but the result is 2 sine x cos x. All right, sine of x plus x would be sine x cos x plus cos x sine x, if you think of it as the sum identity. And then you combine the like terms to get this. So while it's true that in its original form, differentiation here would require the chain rule, if I write this out using the double angle identity, I get something I can differentiate using the product rule. Since the original function, sine of 2x, can be written as 2 times the sine of x times the cos of x, I can think of this as a constant times a product and apply the constant multiple rule to the whole thing and the product rule to this piece here. So this would tell me that f primed of x is 2, I'm going to write this out schematically, sine x cos x all primed. I'm going to be a little bit silly about this. I'm going to write out all the steps just to kind of get us back from the weekend. That would be 2 times parentheses sine x cos x primed, popping out the constant 2, right? Because we know constant multiples pop out of derivatives. And now I can use my product rule. Space here. If I apply my product rule, I get 2 and then a big parentheses. And then in here, I'm going to put the result of the product rule applied to that product, sine x cos x all primed. That's sine of x primed times cos of x plus sine of x times cos of x primed. So it's from here to here, I'm using the product rule. We kind of differentiate one function at a time. And this turns out to be pretty nice. The derivative of sine is cosine, so derivative of sine x is cos x. So this is 2, open big parentheses, cos x times cos x plus sine x times the derivative of cos x is negative sine x. Ooh, this pen. All right. I'll be losing my purple pen. And then we can just clean this up. So that's 2 times cosine is cos squared of x. Sine x times negative sine x is minus sine squared of x. And that's your derivative. And if you're familiar with the double angle identity for cosine, you'll see that this can be written in another way. I'll leave it like this for now. I don't want to give you too much to do at once, but product rule with trig functions. Not too bad. Not too bad. Any questions on this guy? Okay. So let's get into the meat of the lesson then. Today is really about the chain rule. There's so many ways to write the chain rule. You know, I prefer the prime notation when it comes to most things. So that's the way I'm going to describe this to you, but I'll also give you the Leibniz notation. What this says is if f and g are differentiable, then the derivative of f of g of x, all right, again in the prime notation, is f prime of g of x. You differentiate the outer function, leaving the inner function alone, and then you multiply by the derivative of the inner function. This is the simplest way to say it. Okay. So that's the chain rule. What this requires is looking at your function and recognizing an outer and an inner guy. Then you differentiate the outer function, kind of thinking of the inner function as the variable or leaving the inner function alone, and then multiply by the derivative of that inner function. So an example, great example, is the one we just did. I'll write it a little bit differently. I'll say calculate d dx of sine of 2x. So in other words, I want to find the derivative of sine of 2x. Same shit we just did. But this time, I'm going to do it using the chain rule. And the name of the game here is to identify your outer and your inner. Sine is the outer function here, and 2x is the inner. In other words, in this notation up here, sine would be f, and 2x would be g. So I want to find the derivative of f of g. So here, by the chain rule, we get that the derivative d dx of sine of 2x should be the derivative of the outer function with the inside left alone. So what's the derivative of sine?
Cosine.
cosine. And then we multiply by the derivative of the inner function. Here, the inner function is 2x, whose derivative is just 2. So this is f primed of g of x, right? Outer function differentiated, but the inner left alone. This is g primed of x. This piece is the f primed of g of x. This piece is like the g primed of x piece. That's what's going on. And the idea of differentiating the outer, leaving the inner alone takes a little bit of thinking. It's not immediately obvious always what that means, but the trig functions are great examples where it's usually fairly clear. Now this is 2 cos 2x. And it's very reasonable at this point to say, well, shit, that doesn't look anything like what I got up here. Up here, I solved that same problem earlier, and I got 2 times cos squared x minus sin squared x. Here, I got 2 times the cosine of 2x. Can anybody explain that? Let's look at Desmos for a moment. All right, I'll begin with cos 2x. Here it is. It's the regular cosine wave. It's just been smushed in by a factor of 2. So instead of having a period of 2 pi, it has a period of pi. All right, so we go through one full cycle here in half the time. Here's cos squared x. It's a little funky looking. Here's cos squared x minus sine squared x. They're the same. It's the same function. That's the double angle identity for cosine. This really is 2 cos 2x by the double angle identity for cosine. It says cos of 2x is cos squared x minus sine squared x. So it doesn't look like it, but we actually got the same answer both ways. The trick to seeing that is the double angle identity. I like this more than this. This is a little spooky looking to me. This is tractable. I know how to graph this. I don't know how to graph this right away. Right? In your trigonometry classes, you learned how to graph this function. It's a cosine wave whose amplitude is 2 and whose period is pi, because you take 2 pi and divide by this number. So I prefer the answer we get from the chain rule here to the answer we get using the product rule here. And that's just one of the advantages of the chain rule. Any questions on how we applied the chain rule here, or what the chain rule is saying here? Okay, then let's keep playing. Let's calculate the derivative of let's go gentle again. Cosine of x squared. Again, the idea is to think of this as an outer function and an inner function. So the outer function is the cosine, and the inner function is x squared. So to calculate this derivative, I will differentiate the outer function, leaving the inside alone. So the derivative of cosine is negative sine. So that's negative sine of x squared. And then multiply by the derivative of the inner function. Well, the derivative of x squared is 2x. That's it. That's it. There's nothing more to it. And it might seem like a very simple rule, but there is some subtlety. Let me show you one more somewhat gentle example, and then we'll start seeing how these can get a bit more complicated. Any questions on this one?
So I assume as the final result, you would write negative 2x sine of x squared.
Yeah,
I'm just curious.
No,
Okay.
no, you nailed it. I was just about to say before we left here, I would probably rewrite this as negative 2x sine of x squared, just because it looks nicer that way, and the tradition is to put the polynomial piece out front. Yeah, perfect. Okay. So the very first one we could have done either way. This last one, we need the chain rule. There's no way to attack this with identities because there is no nice identity for the cosine of x squared. This is another example of a problem we could solve multiple ways. So let's find f primed of x, where f of x is 2x plus 1 squared. And you saw some stuff like this early on, right? Like as soon as we had the power rule, we were dealing with stuff like this. In fact, you might have seen some things like this back in chapter 2. You can attack this by foiling everything out and then using the power rule. That's one option. So multiply out, use power rule. How would that look? Well, here, if I go to multiply this out, that's 2x plus 1 times 2x plus 1. I suppose you could use the product rule here if you wanted. But if you just distribute everything, that's 4x squared plus 4x plus 1. So f primed by the power rule would be 8x plus 8. Not too bad. Option 2 would be to use the chain rule. You have to think a little bit about what the inner and outer functions are here. So what is my inner and what is my outer function here? This is what plugged into what?
Your outer is the square.
Yeah, very good. The square is the outer function. It's as though I've taken x squared and then plugged in 2x plus 1. Very good. So f prime, it would be d dx of 2x plus 1 all squared. And by the chain rule, I would differentiate the outer function, leaving the inside alone. and the outer is the square. So that would be 2 times 2x plus 1 to the 1. There's the derivative of the outer with the inner left alone. And then we would multiply by the derivative of the inner function. The derivative of 2x plus 1 is just 2. So what do I get? Well, 2 times 2, this is 4 times 2x plus 1. Oh, which makes me think I made a mistake. Yeah, I did make a mistake. If you distribute that 4, you get 8x plus 4. Does anybody see the mistake? We pretend like I did this on purpose as a teachable moment, right? What's the error here?
Distributed before multiplying.
The error is from your previous whenever you took the power rule.
Good. What should this be?
The 8x plus 4.
Yeah, the derivative of 4x isn't 8. This is derivative of 4x squared is 8x. The derivative of 4x is 4. Yeah. And so you see, modulo my mistakes, you do get the same thing. The purpose of this isn't that the right way to differentiate this function is one or the other. I mean, you did notice I made a mistake here, so maybe the chain rule is the better way to do it, right? But the real reason to think about examples like this is if I had something like that. Technically, you could still do it both ways. Right? Mathematicians might argue that neither is better than the other, but if you actually sit them down and ask them to compute the derivative, they're all going to use the chain rule. Why? Why should I use the chain rule for the function at the bottom instead of option 1 there?
Quicker.
Yeah. I would go ahead and make the claim that nobody in this room, myself included, has ever taken the time to multiply something like this out 2022 times, ever. And probably none of us ever will, and certainly none of us ever should. Option 1 still exists here. But like Jai said in chat, you could multiply this out. And what you would get would be, well, let's see, 2x plus 1 times 2x plus 1 times 2x plus 1 times, oh my God, I'm gonna die. There are literally thousands of these things that I would need to FOIL out. That's a big hard nope from me. No thanks. No way. No way. But if we use the chain rule, well, then you can calculate it right away. F primed of x would be ddx of 2x plus 1 to the 2022. Again, the power is the outer function here. So I apply the power rule to the outer part, leaving the inside alone, meaning I bring the power down and I subtract 1 from the power. And then I multiply by the derivative of the inside, which is still just 2. And you would get 4044 times 2x plus 1 raised to the 21st power. Way better. No contest. So sometimes with trig functions and the like, you don't have a choice. You must use the chain rule. With powers of polynomials or powers of multinomial factors, you do have a choice. You can multiply them out. You could write out the product and then use the product rule. But if the power of the factor is large, then doing any of that other stuff is crazy. Just use the chain rule. And I would argue that the chain rule is the superior method, even for the simpler problems, like as evidenced by me making a mistake here, but not here. Okay, so that's what the chain rule is, and this is kind of why we like it. There are some functions that we can't differentiate without it, and there are many functions that are much nicer to differentiate with it rather than applying some tricks like double angle identities or foiling things out or whatever. The chain rule combines with the other rules, not just the power rule. So what I would like to show you is some mechanisms for combining the chain rule with the other rules. Also some kind of very important, very standard derivatives that show up a lot we need to look at. So let's do a bit of that. Let's do a tangent line problem. Let's find the equation of the tangent line to the function f of x equals, how about x times the sine of e to the x at the point where, no, let's see, none of this is going to be nice, is it? Zero. Okay. As with all tangent line problems, we need two things. We need a point and a slope, right? If I'm going to find the equation of any line, point and a slope is sufficient. The point is the first thing I'll cook up. We know that that is going to be 0, comma f of 0, right? We're working at x equals 0, and the point of tangency is always the point on the graph. F of 0, that would be 0 times the sine of e to the 0, which is 0 times the sine of 1. The sine of 1 is an unpleasant number, but when you multiply anything by 0, you get 0. Apologies, somebody just knocked on my door. I'll be right back. Okay, sorry about that, guys. Folks showing up to work on the roof. The landlord is finally trying to sell the place out from under us. So that point is going to be 0, comma 0. Because f of 0 is 0. The slope is the part where we need to do some work, of course. the slope is going to be f primed of 0. So we need to cook up our derivative and then plug in 0 for x. The derivative of this function is going to require two rules applied together. This is a product, right? X times the sine of e to the x. And then the sine of e to the x, that is a composite function. That's like sine with e to the x plugged in. So to find f primed of 0, I need f primed of x, that is d dx of x times the sine of e to the x. To see which order you should apply the rules in, you kind of need to think about what the outermost operation is. So this product is the outermost operation. This is not a composite with a product inside. This is a product where one of the pieces is a composite. So we first use the product rule. So this would be x primed times the sine of e to the x plus x times the sine of e to the x all primed. And then this piece requires the chain rule. So here we're using a product rule. X primed is 1, so we just get the sine of e to the x here plus x times, and now here is where I'm going to use my chain rule. To differentiate the sine of e to the x, again, you need to figure out your inner and your outer. So my outer function here is the sine function. My inner function here is e to the x. So that would be the derivative of the outer with the inner left alone. That's the cosine of e to the x times the derivative of the inner. And the derivative of e to the x is just e to the x. And we could write this a little bit more neatly as the sine of e to the x plus x e to the x cosine of e to the x. And that's as nice as this is going to get. So we've used the product rule in the first step and the chain rule in the second step. Now I'm ready to cook up my slope, which I know is f primed of 0. So I'm just going to plug in 0 for x. That would be the sine of e to the 0 plus 0 e to the 0 cosine of e to the 0. E to the 0 is 1. So this is the sine of 1 plus 0 times 1 times the cosine of 1. So plus 0, right? Because this we're multiplying by 0. In other words, just the sine of 1. And that's not a nice number. You could use a calculator to approximate it as a decimal if you want, but we should just leave it as the sine of 1, right? That's the exact value. So our tangent line is y minus the y value at my point, which is 0, equals m, which is the sine of 1, times x minus the x value at our point, which is also 0. In other words, y equals the sine of 1 times x. And that's a pretty funky looking line, but it is a line. Any questions on the derivative calculation, the stuff here?
for most problems like this, it's product, you should use the product rule first, right?
So it really does depend on the problem we're looking at, but this is outermost a product, and then one of the pieces in that product is a composite, so product rule comes first. I can show you an example where it goes the other way. But sort of ask yourself, what is the outermost operation going on? If that is a multiplication, then the first thing you would apply is a product rule, and within that, a chain rule. It's a good question, and I think the easiest way to answer that, besides the words I just gave, is with a little bit of practice, which we will do. Other questions on the derivative calculation here? Okay, let's take a quick look in Desmos. I think this is a fun, weird function to look at. So we had x times the sine of e to the x. Crazy stuff. So what's going on here? The sine of e to the x on its own is a sine wave who oscillates faster and faster as you go further and further to the right, because the inside of the sine function is getting bigger and bigger. And then when you multiply by x, that's like the amplitude grows as x gets bigger and bigger. But we're looking not at any of that craziness. We're looking right over here at x equals 0. And if you enter our line, y equals the sine of 1 times x, you do see, oh, that's the tangent line. This green line is indeed tangent to that red curve at 0. So, pretty wild function. All right. Let's look at something where we would use a pair of rules, but kind of in a different order like that. This time, rather than doing a whole tangent line thing, let's just find, we'll call it capital F this time, capital F prime, where capital F of x is, how about the tangent of, what would be fun in here? Sure, we'll do it like this. Tangent of x e to the x. So again, we do have a composite and a product. This time, though, the sort of outermost thing going on is the composite, right? The product, x times e to the x, is inside the tangent function. So if I had to look at this and ask kind of what are the layers here, the outer layer is the tangent function. And then inside of that, I have something that would require a product rule, x times e to the x. So like the last problem, we will need both the chain rule and the product rule here. And like the last one, I'm going to diagram the outer step using the prime schematics. So chain rule gets applied first this time. And the derivative of tangent is secant squared. So I'll differentiate the outer, leaving the inside alone. And then I need to multiply by the derivative of the inner function, which is x e to the x. I'll just write it like this. So the derivative of the tangent is secant squared, and we leave the inside alone. So we get secant squared of x e to the x, and then we need to multiply by the derivative of the inner, and this is by the chain rule. Now to differentiate x e to the x, to compute this derivative, here is where I need the product rule. So this is the derivative of x, which is 1 times e to the x, plus x times the derivative of e to the x, which is e to the x. And we can clean this up quite a bit. Not that there's anything wrong with the way it's written now. But I can factor in e to the x here, and what would be left is 1 plus x. And then traditionally, we'd put this whole apparatus out front. So this is 1 plus x times e to the x times secant squared of x e to the x. Okay. So chain rule in the first step, product rule in the second. One of the nice things about the chain rule is that it can save you from having to ever use the quotient rule. And that's one of my favorite things about it. It actually allows us a nice avenue to prove the quotient rule. And it also gives us kind of through that avenue a means to avoid ever using the quotient rule, which isn't to say you should never use the quotient rule. But you can escape it if you want to by cleverly using the chain rule. Every quotient can be thought of as a product of some function and a composite function. One other little neat note here is that there are some functions where the inner and the outer can be a little tougher to spot. So before maybe I talk about cleverly avoiding the quotient rule, from those powers of polynomials, it's easy to get into our head this idea that the power is always the outer function. That's not true. And the most meaningful counterexample there are exponentials. So the way to think of this function, e to the 2x, is as e to the x with 2x swapped in. So your outer function here is like the exponential, e to the, and your inner function here is the 2x. So like this is your outer, and this is your inner. So if we wanted to differentiate this using the chain rule, which is the only way we could do it, we would get the derivative of the outer with the inner left alone, which is going to be e to the 2x times the derivative of the inside, which is the derivative of 2x. Now the derivative of 2x is just 2, so this is 2 e to the 2x. And this is where I give you a kind of general use formula. If you want to differentiate e to some stuff, where u is a function of x, then this will be e to the u times u primed. And then the idea here, of course, is we're assuming u is some function of x, right? You don't need to memorize this as its own thing, but in recent semesters, I've had a few students struggle a little bit with spotting the inner and outer for exponentials, and this sometimes makes it easier to see, just thinking of it that way. So one more quick example here. Calculate f primed of x, where f of x is this very famous curve, e to the negative x squared, like this. Again, the outer function is the exponential. That is the outermost thing going on. If you had to plug a number into this, the last thing you would do is raise e to some number, right? You would take that number, you would square it, then make that negative, then raise e to that power. So the outermost thing going on here is the exponential. This means that when I go to differentiate this, I'm thinking of u as being like negative x squared. So by the chain rule, the derivative here would be e to the u, e to the negative x squared times u primed, the derivative of negative x squared. Since the derivative of negative x squared is negative 2x, you get negative 2x times e to the negative x squared. Again, moving the polynomial piece out front where it looks better. Okay. Let's talk about the quotient rule for a minute. When I showed you the quotient rule, I didn't prove it, right? There's a link to the proof in the modules. I said you can look at it there. It's symbol juggling, it's meaningless garbage, but I will prove it for you once we have the chain rule, because there's a nice proof that uses the chain rule. I mean that. The standard proof for the quotient rule really is just moving symbols around. It's not fun. But if you contextualize quotients as products, proving the quotient rule and avoiding its use, right? If you finished the homework from last week, you are aware, acutely aware, of how unpleasant the quotient rule can be to work with. So here's the idea. If capital F of x is a quotient, say little f over little g, I can think of that as f of x times 1 over g of x, right? That's kosher algebra. And I can think of that as f of x times parentheses g of x all raised to the negative first power. And like our third example, this is a product, one thing times another thing, where the other thing is a composite. This is the inner, this is the outer. So by the product rule, big F primed would be the derivative of the first times the second left alone, plus the first left alone times the derivative of the second. And the big bracketed derivative at the end there, well, damn if that isn't just ready for the chain rule. Let's do it. This is f primed of x times g of x to the negative first plus f of x times, let's take our derivative here. My outer function here is the power, my inner function is g. So I differentiate the power, leaving the inside alone, and I get -1 times g of x to the -2. And by the chain rule, we multiply by the derivative of the inner. Well, the inner is just g, so that derivative is g primed. And at the moment, this does not look a whole lot like the quotient rule, but it is. You see, if we use the same sort of simplification procedures we've been using elsewhere on this apparatus, first let me say here, f prime times g to the -1, that's f prime of x over g of x. I've got this -1 factor in here, which will make that plus into a minus. I've got f times g primed. And then I've got g of x raised to the -2, that's over g of x all squared. And then the only thing to do to arrive at our full quotient rule is to have a common denominator. This guy has denominator g of x all squared. This guy has denominator g of x. So if you multiply by g of x over g of x in this first fraction, you get g of x times f primed of x minus f of x times g primed of x, both of which now have denominator g of x all squared. So you can write that as the single fraction g f prime minus f g prime over g squared, which is the quotient rule. All right, so one, it's a proof of the quotient rule, which is nice. We like to have proofs of our theorems. Two, it provides a way to avoid using the quotient rule if you want to. Sometimes it's absolutely the right thing to do. For example, ask you to differentiate 1 over e to the x, you could use the quotient rule. You sure could, but you really shouldn't. Because 1 over e to the x is the same as e to the x to the -1st power, which is e to the -x. The algebra rule there, one we've used before, a to the b, all to the c, is a to the b times c. Super useful algebra rule. So you can differentiate this straight up with the chain rule and never touch the quotient rule. Derivative of e to the -x is e to the -x times the derivative of -x by the chain rule. Derivative of -x is -1, so this is negative e to the -x. It's like a one-line thing, and I'm writing even more than you need to. Way rather do this than apply the quotient rule to this mess. It gets better. What if I wanted to differentiate I don't know, how about x over x squared plus 1? Okay, could use the quotient rule. That's an option. This definitely looks like a quotient rule kind of thing. I can't split up this fraction and sneak in my power rule, right? Because the denominator has more than one term. There's no nice way to split this up. If you wanted to do this with the quotient rule, I would say I've got no problem with that. Totally reasonable thing to do. But if, like me, you have an allergy to the quotient rule, it just makes you a little sniffly and unhappy, then you could say this is x times x squared plus 1 to the negative first power. Same thing. Same thing, right? Having this factor x squared plus 1 downstairs is the same as having this factor x squared plus 1 to the negative first upstairs. So applying the product rule, I would get the derivative of x times x squared plus 1 to the negative 1 plus x times the derivative of x squared plus 1 to the negative 1. The derivative of x is just 1, so this would be x squared plus 1 to the negative first plus x times, and now here's where I need my chain rule. That would be negative 1 times x squared plus 1 to the negative 2 times the derivative of x squared plus 1, which is 2x. Is this nicer than using the chain rule, or sorry, than using the quotient rule? It's a matter of taste. What sort of algebra do you like to do? You're free to do it either way. This is 1 over x squared plus 1 minus x. All right, so this minus 1 makes the minus. X times 2x is 2x squared over x squared plus 1 quantity squared. Totally a matter of taste, which one you prefer. Just an example as to how you can avoid the quotient rule if you want. If your quotient is made up out of a polynomial and an exponential, one upstairs, one downstairs, then certainly this trick is the way to go. If your quotient is a polynomial over a polynomial, unless you can split it up and use the power rule, then it really doesn't matter. The quotient rule or this trick with the product and chain rule, it doesn't much matter. Okay. We are just about out of time for the day, and I feel like we've looked at plenty of examples here, but let me just see if there's anything cute or clever in the textbook that we could use for a good closer. Yeah, I suppose we could look at something like that. I've done some stuff like that. Oops, so the chain rule is nice. Let's do. Yeah, I got one. All right. So one last guy to finish things up. This isn't anything special. Let's find the slope of the tangent line to the curve f of x equals the square root of 1 minus x squared when x is equal to the square root of 2 over 2. So I don't want the whole tangent line, just its slope. For that, I need f primed, which would be the derivative of this function, square root 1 minus x squared. Important note here, the square root does not distribute. This is not the same as 1 minus x. This again, this is not 1 minus x. Can't do that. That shit never works. But the square root is the same as a 1/2 power, and although that power does not distribute, that will show me how to handle this in the context of the chain rule. The power is the outer function here, and the 1 minus x squared is the inner function. So this would be 1/2 times 1 minus x squared to the 1/2 minus 1 is -1/2 times the derivative of 1 minus x squared, which I'll just write as that primed for the moment. And you notice anytime I've got to go like multiple layers deep, I'm using one rule within another rule, I always write the first one out just like with the next guy set up, but not actually trying to compute this at the same time. I really encourage you to do the same. Try to do one thing at a time. And then you just look back and say, okay, where am I now? Well, I've got this 1/2 times 1 minus x squared to the -1/2. And then I still need to differentiate 1 minus x squared. Well, the 1 differentiates to 0, negative x squared differentiates to -2x. And then this 1/2 can multiply with this -2. They will cancel. You'll have -x. And then 1 minus x squared to the -1/2. I can write that as over the square root of 1 minus x squared. And that's it. So if we want the slope of the tangent line, that would be f primed evaluated at √2/2, which would be -√2/2 divided by the square root of 1 minus √2/2 squared, which is -√2/2 divided by, when you square √2/2, you get 2/4, or 1/2. So that's the square root of 1 minus 1/2. Which is -√2/2 divided by the square root of 1/2. This might not look like a nice number, but it is actually a very nice number. Let me continue down here. You've got your -√2/2. And then I'm going to multiply by the reciprocal of the square root of 1/2, which is the square root of 2/1. So that's negative square root of 2/2 times square root of 2/1, taking the square root of the top and the bottom separately, which is -√2 times √2/2, which is just -1. And what we've really done here is we found the slope of the tangent to the unit circle at the point associated with the angle pi/4. You know that tangent is -1. Slope -1, I should say. But that's it. That's it from me for today. That is the chain rule. So it's not a terribly hard thing to use in simple cases, but it can get complex, can get a little bit tricky, especially when you start to layer it with other rules. So you've got a homework set and a study guide up. I recommend beginning on both as soon as you can. The homework is just chain rule stuff. So I'd work some of those problems until you get comfy, and maybe then pivot to the study guide. Try to get the study guide submitted, the written work submitted before Friday. If you submit it before Friday, I will get you at least some feedback on that work before the exam on Monday of next week. That's it from me. Do you guys have any questions before we wrap up here for today? Alrighty then, on Wednesday, we'll do a little bit more practice with the chain rule, and then Friday we will review for the test. So Friday is going to be a review day. You can bring any questions you want to talk about. And that's the game plan, gang. So I will leave it here. If you want to talk to me, of course, office hours, Discord, email, Canvas, you all know the drill. Please, if you are struggling at all, if you're falling behind, or if you're in a place where you're concerned that this test is not going to go well for you, don't let this week go by without coming to office hours and talking to me. If you're feeling nervous, I want to hear from you so we can try to get you set up well for the test. But that's it. I'll see you guys on Wednesday.